Hey everyone, this is Alex Davis speaking, and welcome to the first in a short series of videos about the physics of disk flight. So, in these videos, we're going to discuss the physics and the necessary mathematics in order to understand the behavior of a rotationally stabilized aerofoil. What that means is we're going to look at different disks, be it ultrastars, Innova pulsars, Wama frisbees, or disc golf disks. They're all governed by the same set of equations. And when you understand that, then the differences, sometimes very radical differences in their behaviors, become somewhat intuitive. We're also going to look at different wind conditions, wind speeds and directions, and how they interact with the edges that we apply to the disk and the spin. Because all of those combine to produce slightly different effects, or sometimes in certain circumstances, very conspicuous effects. When you have that knowledge, you're in a position to better maximize your potential. You can make adjustments to get the most out of your different throws, and you can find ways to leverage different situations to get exactly the outcome that you wanted. Now, why should you study something in this much depth? Well, I'd like to explain it using this analogy. You do not need to understand how your transmission works or your engine works in order to drive a car. You can get by day-to-day functionally without that knowledge. But if you ever want to become an elite-level race car driver, you should probably master at least an elementary understanding about how these things actually function. Now, the first thing that we're going to need in order to discuss this kind of motion is a notation that allows us to communicate commonly about what it is we mean. Now, a very long time ago, people discovered the hard way that it wasn't very convenient to be drawing swirls on paper to describe rotational motion or to resolve the mathematics. But a notation that did work very well was to use the right-hand rule to communicate different rotational motions. The way the right-hand rule works is very simple. If my thumb is pointing in the direction of the vector, then the natural curvature of my fingers governs the rotation. If my thumb is up, then the spin, seen from above, is counterclockwise. And this is true for any arbitrary number of directions. This is a three-dimensional universe, and you can have rotation around different axes. So, we're going to need an orthonormal basis of three vectors. It's not as bad as it sounds. In this coordinate system, we have three orthonormal vectors. That means that they're all the same length, and they are at 90 degrees with respect to each other. It's a very convenient vector basis for communicating things in the universe that you and I interact with.
This is what the ijk vectors look like applied to a disk, where they represent both linear and rotational vectors. That is, the pitch, roll, and spin axes.
Now, we are going to have to use some kind of rule for multiplication. And in angular momentum and rotational dynamics, what you wind up using a lot of the time is called the cross product. Cross multiplication is just multiplication with an additional rule about how you resolve the directions of the resultant vectors. So, the right-hand rule in a right-handed coordinate system says that you resolve it this way. If I take the blue vector and I want to multiply it by the pink vector using cross multiplication, I point my fingers in the direction of blue, I turn my palm towards pink, and my thumb is now pointing in the direction of the resultant product. In this case, in the yellow direction. And that's what a right-handed orthonormal vector basis looks like. Blue cross pink gives yellow. Conventionally, in mathematics, the way we describe this is I cross j is positive k. J cross I is negative k. That's your right-handed coordinate system.
The cross products apply equally to both the linear and the angular sense of all three vectors I, j, and k. Here I've listed all the possible cross products of all the unit vectors.
So, the last thing that you need to know is where my vectors are going to be pointed in space. I could just leave them floating while my disk travels through space, but it's not very convenient. It's a lot easier to attach my reference frame to the disk in flight. So I'm often going to say that I, or the blue vector, is always in the direction of flight. And I'm going to say that k is in the direction of spin, coming up out of the disk. When I tend to say that something is spin up, I mean that it has the spin of a righty forehand. When I say that it's spin down, that means that it has the spin of a righty backhand. And I'm saying that it's down because it's negative k, and it's spin up because it's positive k. Pretty intuitive. All right, that's all you really need to know about the vector math. And when you're ready, tune in for some rotational dynamics.
So, in summary, we have the right-hand rule governing rotational motion, a vector basis of three vectors, I, j, and k, and all the cross products for all three vectors.